And welcome to this afternoon's webinar. I'm Nick Holt, editor of AMS, and today's session will be hosted by Comau, who will be focusing on advanced multi-material joining and explaining how early involvement in engineering will deliver the best manufacturing solution. Today's presenter is Martin Kinsella. He's Advanced Materials and Process Technologies Director for Comau. And Martin has over 30 years in the automation industry, joining Comau in 1990. In 2000, he became engineering manager, responsible for aspects including R&D, simultaneous engineering, RobCAD, and the virtual factory. And in 2012, he became director of Advanced Materials and Process Technologies. Now, Comau has established an advanced materials core sector within its business unit, and Martin is responsible for creating the Global Centre of Excellence's Advanced Materials. If you have any questions during Martin's presentation, please type them into the box in the corner of your screen, and we will answer these in the Q&A session at the very end. If you experience any technical difficulties during the webinar, again, please type your queries into the question box, and our team here will do their best to resolve these for you. So without further ado, I will hand over to Martin. Thank you.
Thank you, Nick, for that introduction, and welcome and good morning, good afternoon and good evening, depending upon where the people are calling in from. Brief introduction to myself. As Nick says, my name's Martin Kinsella, Advanced Materials and Process Technology Director for Comau Group. Thank you for taking time out of your busy schedules today in terms of dialing into the webinar. Today's presentation, I'll take you through a certain series of slides that reflect the multi-materials being currently used in the industry, and also a number of joining processes. We'll basically have a brief presentation about Comau at the start, for those of you who don't know, and then we'll go into the main presentation. So thank you, and we'll make a start. So Comau Global Company, we are a leading provider of advanced material systems and innovative sustainable automation and service solutions. We have a strong history in the automotive industry, and we have continued to grow and today offer skills and know-how to a wide range of industry and applications. Our distinctive strategy is split up into a number of areas. We are solution-orientated in terms of using the best automation to deliver a key range of technologies, fully integrated from product, process and service. We're a global company. We have approximately 23 centres located in 16 countries. We follow the PMI process so that all regions and all locations operate under the same standard processes. Innovative in terms of high-density automation solutions, energy saving, we have eComau as part of the group, and also lean production approach. We offer a wide number of products and solutions in the body construction area in particular. These range from framing systems, accumulating conveyors, vision systems. We manufacture our own welding guns, AGVs, etc. Flexible systems and solutions in terms of multi-vehicle processes. These can range up to 8 and 9 variants if within one assembly process. Technologies ranging from, but not only including, laser welding, resistance spot welding, mechanical joining, and roller hemming. So the Comau Global Map. Comau is developing a comprehensive advanced materials strategy that focuses on a combination of efficient designs, principles, and capabilities to join premium materials such as aluminium, high-strength steels, press-hardened steels, carbon fibre, composites, magnesiums, etc. Our technology centres have demonstrated and are currently working on a number of developments that are leading edge in the medium and high-volume manufacturing environment. As you can see, we have currently 3 centres, one in Detroit, which I'm actually based in Detroit currently. We have a centre in Turin, and we also have a centre in Shanghai. So why are we talking about advanced materials and new technology? As everyone's aware, there's a global challenge to meet the CO2 demand that's been government driven. As you can see here on the left, we have a graph showing the actual demand for 2025 across the globe, and it's globally recognised both in Europe, Asia and in the Americas. Okay, and therefore every OEM is being driven towards a target. So it's not just a an internal target, it's a national and international target. As we can see here, if we took a typical CD segment vehicle, if we estimate about 1,500 kilograms, you can see from a breakdown the approximate body shell-less doors equates for approximately 50% of the vehicle total mass. If we can make a reduction of approximately 10% in that mass, that then gives us an approximate 3 to 4% economy improvement, which therefore is then driving towards and heading towards the target for 2025. Here on the right, you can see that based on a typical mass being, if we target approximately 400 kilograms, if we stayed with current steel manufacturing, we'd be targeting about 400 kilograms. And you can see then with the use of optimized steels, aluminium, magnesiums, carbon fiber reinforced plastic, etc., these can dramatically reduce the overall mass of the vehicle. But at the same time, there's a cost implication. So what we're going to talk about now is some of those costs and some of those processes. The materials picture, as you can see, there are many, many materials, and this is only to name a few that are currently in both low, medium and high volume manufacture. Aluminium, hybrids, magnesiums, composites, plastics and steel. Steel has its own subsection in terms of high strength and various other dual phase, etc. materials, okay, which form a number of vehicle and body assembly types. And these are joined by a number of process combinations. So this can be spot welding, riveting, flow drill screw, projection welding and bonding, etc. So this is just to give a small picture of the available opportunities in which we can join these materials. Each manufacturer is now kind of reviewing their product in terms of their overall weight position. So we've taken a steel underbody or unibody, yeah, what used to be the common practice. And now, as you can see, there's a large number of different processes and different materials being incorporated to bring this multi-material concept, which is now becoming a reality. There are now many vehicles on the road that are encompassing a wide range of materials. On the right here, we're just showing some of the lightweight materials and what materials they could potentially replace and the approximate mass reduction. So, for example, aluminium currently being used to look at steel or cast iron. This gives an approximate 40 to 60% mass saving. Advanced high-strength steels, which are still very common, are replacing mild steels and carbon steels, giving a lesser figure of about 15 to 25%. So, materials such as high-strength steel, aluminium and composites, and to a lesser extent magnesium, have been utilised over the years. Yeah, while mild steel has seen a steady decline. Okay, as the new materials are introduced and adopted, the workforce needs to adjust and accommodate to these new processes. This is giving greater focus on systems approach to vehicle design, greater emphasis on the characterisation of the actual materials and their properties, the interaction of mixed materials, aluminium to steel, steel to composite, aluminium to magnesium, etc. And also given a wider range of manufacturing processes, some of which we'll describe later in the presentation, and also a much greater use of computer-aided engineering. This multi-material approach, while utilising the steel-only body in white, this can achieve maybe a reduction of about 20%, whereas the multi-material approach can give up to about 40%. This is used in high-strength steels, magnesium, and composites, etc. The multi-material approach is being extensively applied to nearly every OEM in their current assembly process. But the assembly systems are cost-sensitive to the product. So now the product is driving in terms of its cost makeup. Here we have some examples on the right, just showing in terms of early simultaneous engineering and product interaction with the product designers, using the different processes in terms of, for example, here we're looking at rivet manufacturing, yeah, looking at early configuration of product. By this early engagement with the product design team, changes can be made in the CAD environment that have very little or no effect later on downstream. So this is where the key engagement early on is vital to the process, because they're very cost sensitive. The most critical aspect of manufacturing a vehicle today is still cost. With traditional steel materials, the manufacturing parameters are well established and have been for many years, and only partial parameters exist for the introduction of advanced materials and associated processes. Most automotive manufacturers have engaged in lightweight assemblies, particularly for closures, for example, and the move to the complete body has been done in only a number of applications and is not yet commonplace. It is in the product evolution that the final real cost of the model exists. The transition of the product to a robust and medium and high volume manufacturing solution will depend upon the integration into the product team of the manufacturing engineers who best understand the final solution. So this is where we're advocating the early engagement in terms of product design with the assembly teams and manufacturing teams, who can then impact and influence the actual product. Later on, and in the slides, we're going to talk about some joining technologies. Here's just a brief example of some of the technologies we're going to be discussing. The ones highlighted are asterisks. These are relatively or very familiar, depending upon their actual process, in the steel environment. Yeah, their application in advanced materials is different and unique, and certain characteristics that were well known for many years are now being developed and introduced and investigated. One of the particular common features now in terms of advanced materials, and in particular aluminium, is self-pierce rivets. So this is a structural joining process for producing a lap joint between multi-material layers, and it's forcing a tubular steel rivet through the upper section, and as you can see, it then starts to flare the material into this die cavity. That then produces a mechanical interlock. Okay, here we have a typical cross section of the SPR, and here we have a gun. So it's a servo-driven gun. This particular one is mag feed, but there can also be spool fed. Mag feed solution gives the ability to actually apply 2 rivets on a similar process. The actual self-pierce rivet is key to the process. Here we're showing a couple of key examples of different types of rivets. Although they may look very similar, their interaction with the particular stack-ups and in particular the materials and the thicknesses, etc., is key to a robust process. So this is the absolute critical item when we're engaged in self-pierce riveting, is understanding the stack, the materials, the properties of the materials, the coatings and the materials, etc. This is key to a robust process. Here we have some preferred joint configurations. So preferred is thick to thin, yeah, where the bottom percent is greater than 30% of the overall stack, gives better strength consistency. Non-preferred, thick to thin, where this gives a lower strength and also sometimes causes, in terms of the rivet, breakthrough on the lower edge, which obviously then gives a quality problem. A brief summary in terms of the SPR, self-pierce riveting. There are normally 2 rivet diameters, 3 and 5, but there are some other bespoke rivet diameters. Some current summary in terms of minimum widths, so 16 and 19 mil. Center line to trim edge is quite reduced down to 7 and 9 mil. Maximum stack joints, 3 to 5 for the 3 mil and 5 to 9 for the 5 mil. But again, emphasizing that the stack and configuration is critical to the process. Preferred joint direction is steel into aluminium or hard into soft. 2 thickness and 3 thickness joint stacks are possible. The maximum steel grades currently self-pierced or utilized for self-pierced riveting is around about DP 800 and 600. But there are new stacks that are currently in development. Okay. On the underneath of the actual rivet, there is let's say, the depression or the outfeed. This is approximately 2 mil, and this needs to be considered when overlaying parts on top of each other and also in the actual automated process. Flow drill screws. So this is a single-sided joining technique. Friction created by the high-speed rotation of the screw transforms the parent material into a plastic state. Then there's an application of force, and then that actually forms the thread down the lower edge of the material, as you can see, and the plasticated material also flows up into the upper cavity of the flow drill screw. The flow drill screw design and the material stack-ups, again, not as critical as self-pierce riveting, but does need to be considered and fully understood when processing. Typical joint configuration. This is showing a lap joint with an overlap of approximately 16 mil, 20 mil to the edge if there's adhesive. 7 mil clearance holes required sometimes on the top sheet, depending upon the actual stack-up configuration. And a 10 mil clearance hole, depending on the tooling variability, etc., in the lower sheets. This is just showing a typical mounting example where we've got the spindle. This is mounted onto a robot. Okay. During the actual process, a significant amount of force is applied, and this has to be absorbed by the robots in its mounting. So the mounting should be linear to the axis for low loads on 5 and 6. Yeah, the feed tube should be unrestricted to ensure no collapsing or feed issues. And the robot supplier should always sign off the application, but normally a minimum of a capacity carrying robot of approximately 350 kilograms is required. Here we're just showing some of the testing we're doing currently. We've carried out several 100,000 applications of the actual screw. We're doing what we call a 9-panel chart. Here's where we actually document and record mean time between failure, mean time to repair for the actual process, and we do some statistical analysis in terms of time cycle and synthetics. So in summary, it's a 2T joint impossible without a pilot hole. 3 and 4T thicknesses may require a pilot hole depending upon the joint materials. They can join dissimilar materials, steel to carbon, aluminium to carbon, etc. Okay. Insertion force can reach approximately 280 kilonewtons. Peel performance is superior to SPR, and it only requires one-sided access. Resistance spot welding, very common within the motor industry. Most companies have investigated and some have rejected the use of this technology within their aluminium or advanced product. Yeah. One particular OEM has developed a patented process where it actually provides ridges on the top of the textures on the top of the tip profile. This is to break through the oxide film. But there have also been a wide range of significant developments within the weld timer controls technology. Adaptive welding capability to overcome variance is giving very, very good results in the marketplace. And also a variety of processes to maintain and clean the tip surface in conjunction with the timer can produce effective results. Here we've got a 3T stack-up of an aluminium joint, approximately 2 mil material, so totaling approximately 6 mil, giving a robust joining process. Some considerations when actually using resistant spot welding, in particular with aluminium, because of the high currents required, maybe up to 40 or 50,000, okay, it does have an effect on the tooling and the surrounding areas. So the tooling and the fixturing unit shouldn't be within approximately 20 to 70 mil of the actual resistance spot welding position. Other considerations to consider in, for example, a high density facility that's simultaneously joining with different processes. For example, here we've got FDS, resistance spot welding and FDS. A consideration that actually needs to be required in terms of the FDS process and the fact that the depth sensor, which is a key component in the process of the FDS application, requires approximately a 500 mil clearance loop to the nearest resistance spot weld if you're doing it simultaneously. Just a key point to be aware of. We mentioned earlier in the presentation about carbon fibre, and the reason for this slide is just one is to discuss about carbon fibre and its introduction, which is, let's say, more cosmetic historically, but now becoming more commonplace in terms of production medium and also integrating into the high volume. But what this is showing is that the actual, by utilising good design, multi-material and multi-processes can come together. So here, for example, we've got a composite floor, and we've got a steel top and bottom section. But as you can see, the actual lower section has got a depression in it, which allows then the top and bottom material to be joined, which in this instance is showing a resistance weld spot, but could be a self-pierce rivet spot. Okay, so this is showing the creative design early on can actually allow this introduction to take place. Graph on the right here just shows in terms of the different materials, okay, how easy they are to apply or how difficult, and also in terms of the cost implications. So as you can see, when we get into processes such as titanium and carbon fibre, their cost and application is more challenging than we'll say normal mild steel or lesser materials. Okay. As a brief summary, facilities are producing aluminium welds predominantly on closures at this time. There are future programs that are ongoing and developing currently, yeah, where the wide-scale use of resistance spot welding is becoming more extensive. Certain limitations, weld tips must be perpendicular. Normally 2T thicknesses with a few 3T, but more in the future. Isolating of the tooling because of the high currents. Normally a 20mm cap because this helps with heat dispersion. Adhesive between the material will increase the weld current requirements significantly. Example materials, 5000 and 6000 series materials are currently being successfully welded. And stacks up to multiples of 4mm. So in terms of the actual stack configuration, it's quite significant. Well, in terms of schedules, weld cap definition is particularly impacts on the schedule. So any contamination can dramatically affect the actual quality of the weld. Typically about 35K in terms of current, and about six cycles. 50K on the greater materials, depending upon the actual process. Another mechanical joining is a clinching process. So it's a joining of, let's say, sheet metal without any additional components such as rivets or flow drill screws. Special tools to plasticate the actual material. So you can see the material deforms into the lower dissection. Clinching requires an open flange with good access on both sides. Clearance between the center of the joint and the flange, the area should be at least 1.5 times the punch diameter. And the clinch joint should be spaced to avoid deformation of the actual material. And a minimum of 2 to 3 thicknesses is recommended between joints. Here's some summaries in terms of possible joint configurations. As you can see here, we've got two different, we've got the circular and we've got the rectangular. These are used when using heavier materials. Typical materials that can be clinched, low carbon and microalloys, and zinc coated and stainless steels, and lightweight materials such as aluminium because of its ductile properties. Again, another mechanical roller hemming. Here we're actually forming a flange that's encapsulating let's say, an inner material. Here we've got a process where it's no other additional tools are required. It's a relatively simple process, mainly used in closures, and has the roller hemming process has become more commonplace than the traditional tabletop in terms of closures and, for example, hood, doors and decks. Again, adhesives. In certain areas, adhesive bonding is used as a supplementary to the mechanical joints, yeah, or resistance spot welding. It is an absolute essential component in the manufacture of aluminium-intensive vehicles, and it can contribute to approximately 50% of the structure strength of the body in terms of its overall performance. In areas that the adhesive bead is used for sealing, as well as insulation between aluminium and steel, so as to prevent any corrosion. The curing process may also be required. Some critical requirements are, because of the application speed of the actual adhesive, yeah, the overall manufacturing process needs to be fully understood. flexible multi-nozzles for low and medium and high volume solutions. Robot manipulation to heated hose requirements to be assessed in terms of access and durability. Inline metering and dozer of multi-nozzle applications is more commonplace now. An application of vision systems in critical areas to ensure bead shape and location. And as I mentioned earlier, in particular where you've got dissimilar metals being joined together, and the adhesive bond is being used as the separator. Here, it's imperative that a good bond and consistent bond is applied. Laser technology. Another process in terms of joining various materials. Here is just showing some of the different processes in terms of areas of laser welding, and not exclusive to this. So we've got remote laser on the door, brazing on the deck lid, roof joints can be brazed and welded also. This can be steel, aluminium, and becoming more commonplace with aluminium. Advantages: very high process speed, high flexibility, reduced tooling impact, high quality and accuracy, and low residual distortion into the actual product. Can offer higher stiffness, dramatic weight reduction, welding access only from one side, and minimum product deformation after welding because of the low impact. Applications in body and white, because of the zero gap, it's now becoming more commonplace to actually see a brazed joint as the finished product. Welding can be edge or lap joint. Here we've got an example of roof laser welding, and then on the next page then, what we've got is an example of some laser brazing. Can be considered on the roof and the ditch where there are no attachment points for such as a luggage rack or etc. Provides a cosmetically accepted joint even for an A-class surface. So what we have on the right here is, we'll call it a traditional process, where we have the side member, the lower member, and the roof member that have been spot welded together, process of sealer application applied, and then a roof trip molding fixed. So in terms of costs, processing time, etc., quite an extensive and long process. Whereas this is becoming now more commonplace to replace this with a brace joint. So here you can see the side member, the roof design, and the lower member, okay, with just a brazed joint to give the same effect visually and aesthetically as the roof trip molding. So far less complicated in the stamping process, reduced materials, therefore saving on weight and cost. No need for sealers, the robot can be one-sided, and processing speeds up to approximately 6 meters per minute. On the other side, as you can see, a more complicated process in terms of delivery. Remote laser welding offers various shapes in terms of the welds, which can drive the overall weight of the vehicle down. The following two shapes show in terms of 8mm diameter typical spot weld. So with a perforated 18mm or a straight 25mm remote laser weld joint, it's given the typical performance of 8mm diameter spot weld. But what it does do, if you look on the left, it can give dramatic savings in terms of weight. So the flange width required for a resistance spot weld compared to what's required for a laser spot weld is dramatically reduced. So potentially you can reduce the flange length by up to 33%. And here we're showing a typical door opening aperture where the remote laser welding process, if we took at the door, could be used across this process on both the body assembly and the actual closure assembly. Some trends that are currently out there at the moment. So in terms of welding cosmetically, roof to body sides and body sides, and in body and white construction. Here we've got cutting, laser cutting, because from a laser point of view, you can both cosmetically weld, you can do edge and lap joints, remote welding, and also cutting process. So here we're cutting on the body sides, could be a hole for identification or for an aerial, etc. Or it could be the front end or body complete, where we're actually mounting maybe a bumper assembly, etc. Laser braze mainly used on Class A joints and for aluminium will be a filler wire required. Laser edge, not cosmetic, single-sided, mainly used on doors and roof ditches. Remote laser, not for 600 currently, but being evaluated, can be used upon multiple applications. This could be closures, this could be sub-assemblies, etc. And cutting, for example, could be used for model-specific features. I've identified, drawn up, related back to aluminium, because with aluminium stud welding, although there are several types of studs available in the marketplace, there are mainly two types used for aluminium, and that's the earth and fir tree configuration. The reason I've highlighted this in the presentation is when stud welding aluminium, a couple of key points. Ground in the application must be reviewed and must be robust in terms of the contact to provide a good feedback to the system. And aluminium studs require a shielding gas. So as you can see here, there's a flexible shield which then is mounted onto the actual stud welding head, forming a closed loop and retaining the gas, which is normally argon in the process. Here we can see, in terms of stud weld direction, the actual flexible cap is closed now on the part, so it's given a good shielded gas area in terms of application. Here, showing a different approach in terms of angularity, but still giving a robust solution in terms of our process. This is just a simple guideline just to kind of show you can stud weld off angle, but in terms of the process, it needs to be robust and understood. And as you can see, the shield is being compressed to form the airtight circuit. Some alternative joining systems, riveting joining, currently under review by ourselves, not yet in high volume manufacturers in any of the OEMs, but being introduced on a lower scale. High-speed joining, single-side application. So as you can see, similar to a friction stir stud in its looks, but it actually is just fired under force into the two materials. Can be used to join dissimilar materials, so it's quite effective in terms of its process and extremely quick. Solid punch riveting, not widely used currently, but being introduced in certain applications. So in doing so, the actual workpiece are joined, are fixed by the die and a blank holder, okay? And the serrated edge of the rivet forms the material, as you can see, to give a sufficient joint. Yeah. Joints can be joined with the contain adhesive or painted material, okay? Preferred riveting direction is thick to thin and hard to soft. Has a low joining force, so in terms of its application, not very widespread. Friction stir welding, this particular process is becoming more commonplace now, well suited to aluminium applications. High thicknesses can be achieved during the process. Very green, no filler materials required. Can join the similar alloys, okay? Licensed from the Welding Institute in the UK and developed approximately 10 or 15 years ago. Regarded as new technology within the automotive in certain sectors, but it has been around, as I said, for about 10 to 15 years. Mainly used on, let's say, some engine mounts and front structure assemblies. It does require, in terms of force and tooling, some special tooling considerations in the actual process. Friction stir riveting. Again, we're now taking the combination of, let's say, like the flow drill screw and the friction stir process, okay? Used because of the press hardening steels becoming more widespread in the automotive sector, okay? Here we can join aluminium to high press hardened steel, okay? So the actual process actually spins at very high high revolutions, applies a force, and then actually deforms and plasticates the aluminium and then friction welds onto the lower steel material. So not common at the moment, but becoming more used in isolated areas. and can be used and compatible with adhesives. High mechanical strength of the joint allows a reduction in joints in terms of its usage. Plasma transfer wide arc. This is a particular cell that we've developed here within Comau, where again the drive to reduce the overall weight and mass of the vehicle. In here we're actually taking an engine block that would traditionally, the aluminium block, which obviously is a weight saver, but traditionally has had a steel liner in the actual cylinder. So here, this particular process, we were able to eliminate the steel liner and actually, using the process of wire arc transfer, coat the actual aluminium cylinder wall with a very patented process, which gives a very fine wall lining, but is actually harder wearing, more cost effective and longer lasting than the steel lining. And also it's able to reduce the engine temperature overall in the performance. So here we've actually got the wire arc head is actually mounted on the robot, producing the material into the cylinder. What can it do? It's replacing the liner within the engine block with a coating. So we're reducing the cost, rate saving, improved durability, and more flexible in terms of process. Improved thermodynamics, so it's noise reduction, fuel economy and emissions, less packaging, no glaps, and low quality heat capacity. So we're actually reducing the amount of parts being used as well. And also, in terms of the tribology, we're reducing the amount of friction in the actual engine, so we're running more effectively. It's improving the fuel economy, improved durability, and can also be used in the stop-start configuration. Okay. So what does that bring us to? The future. Automotive design is currently investing in different and new materials to respond to both the government and the customer demand for improved fuel economy and reduced overall vehicle cost. This in turn will drive the industry, including the material suppliers, to develop new, stable, cost-effective solutions incorporating a number of joining processes within the body shop, some of which we described earlier in the presentation. There are others which we'd like to and could go into more detail, but due to time constraints and obviously not to take up too much time today, we've just kind of put a small picture together. So now I'd like to hand back to Nick, and we'll maybe do some questions and answers.
Thank you, Martin. That was a really good presentation on multi-material joining. I know that's as you mentioned earlier, it's a huge subject, and I think you've done a good job to cover that in the timescale that you've had. We've got a number of questions here for you, Martin. So I'll begin firing these straight over to you. Going back to your initial discussion on multi-material approach, we've got a question here about would you recommend castings for this approach?
Well, castings, would say, are, let's say, in the traditional design vehicle, they're becoming more widespread. Yeah. So certain areas, such as the suspension mounts in the front engine assembly area, they're becoming very widely used. An area where, in particular, magnesium is now becoming more widespread. Okay. But the introduction of magnesium, it also brings on some other critical items. So in terms of its process, yeah, that particular attention needs to be paid in the actual process of the manufacture of the magnesium die cast, making sure in terms of its robustness, its let's say correct tooling and density of the product, because it needs to be a robust process so as to ensure good joint integrity. And with magnesium nowadays, we're also using and have used a smaller rivet, for example. We're now using a 3mm rivet just because of the material properties. Okay, hope that answered your question.
Thanks, Martin. Moving on, a question relating to self-pierce rivets. It just discusses the talk of aging effects in the process. Could you clarify that?
The use of aluminium has become, let's say, very widespread now in terms of a number of OEMs. But there are some particular characteristics that are, as we described earlier, the difference with the, let's say, the mild steel traditional basis where the components are just pressed, ran off in an assembly line. They can, let's say, as long as they're protected, and don't corrode, they can last a considerable amount of time. But certain aluminiums nowadays actually have what they call an aging. So once they've been processed, treated, etc., they then go into, let's say, they have a shelf life. So certain materials from the, let's say, their point of manufacture have a certain age limit, and let's say, that's maybe 6 to 9 months. So what that then means is logistically and part control becomes more of the day-to-day process when you're using these particular materials. So it needs to be a part of the overall solution of the body shop, that it's understood that these are particular constraints with the material. It still can give a joint, but in terms of its robustness of that joint, it, let's say, deteriorates over a longer period of time. Okay?
Thank you. Again, with self-piercing rivets, can a riveted panel be placed directly on top of a panel?
So if we, I'll try and go back in the presentation, but if you recall, the riveted process has a deformation into the die. So the lower part of the rivet forms what they call a button. The button is approximately 2 mil in depth, and so it's 2 mil below the lower section. So therefore, you've got, let's say, a 2 mil button that needs to either be avoided when you're laying one assembly on top of another assembly. That could be, for example, in cutout. That could be a cutout or a notch, etc. Or it needs to be regarded that there's maybe a clearance hole. So multi-materials and stack-ups can go together, but the button needs to be considered in terms of that assembly process. Again, going back to CAD-CAM being a key component. And what is also key to consider is once you've actually applied the rivet, is that button is, let's say, formed in the die, and if it's in an automated process, the extraction away from that button needs to be considered in the process, so as not to actually cause any damage to the product. Is that okay, Nick?
That's fine. Thanks, Martin. Looking at the question relating to the SDS system, the SDS process, you were discussing some figures regarding the spindle, and the question here is, what is the capacity of a spindle?
There are a number of spindle manufacturers out in the marketplace. Okay, but in terms of, if we took one particular manufacturer, they have up to, let's say, I'm going to score maybe about 500–600 pounds of force. Okay, and that can deliver approximately 15 Newton meter onto the actual screw, and can actually rotate up to approximately 5,000 RPM. So in terms of its capacity, it's an extremely quick process. But as we showed on the slide earlier, although it's a very quick process, there's a definition of approximately anything from between 6 to 12 sequence steps in that actual process, where the process is monitored very, very carefully in terms of its depth, its rotation, and the amount of force being applied in the process. Okay.
Thanks, Martin. Staying with FDS, quite a specific question. What is the preferred feeder type that doesn't generate as much flaking of the flow drill screw? Could you answer that?
A very detailed question. Yes, the flow drill screw, in terms of its manufacture, is similar to the rivet configuration. The rivet and the flow drill screw, they are not just in terms of, let's say, a rivet and a screw. The process in terms of the material used, the coating used, the thickness of the coating, and the very critical manufacturing process is key to the robustness of the joint. Okay, so the actual flow drill screw has a coating on it, and this coating forms part of the process because it actually helps micro lubricate the actual joint. So we would recommend, in terms of let's say the feeder type, it would be, let's say, the scissors type, where you actually have, rather than a bowl rotating with all the flow drill screws rumbling against each other and actually then potentially eroding this coating. The scissor type, the slide type, has a more smoother action. Okay, so that it maintains the screw coating for a longer period of time. So it would be the slide configuration. Okay.
Thanks, Martin. Moving on to laser technology, a question here sort of relating to process and cycle. How long can a product sit in a station after laser cleaning?
What we'd recommend, if cleaning has been part of the original process, is that the laser post-process takes place immediately thereafter. So if for example, there was a major breakdown or a failure, etc., we would recommend that the cleaning process, or let's say after a long period of time in the cells being down or not working, that the cleaning process is repeated if that is part of the particular process, if that is part of the original sequence and process. We recommend it takes place again. All right?
Thanks, Martin. You've generated a lot of interest with this presentation. We've got quite a lot of questions to get through. I'm going to keep firing along for the next sort of 5-10 minutes, if that's okay with you, because as I say, we've got a great deal of interest here from our audience. Question we've got here, Martin, regarding the behaviour of the joints when submitted to vibrations and our environmental temperature variations. How do those joints behave when conditions like that, with vibrations and temperature changes, become a factor?
Well, in terms of the actual, if we took, for example, the resistance spot weld, is the material obviously has a coefficient of adherent expansion, and we've joined the material with the resistance spot weld joint, and its process over that heat and temperature raising from the environment has a limited effect. But where we're joining other materials with different linear coefficient of expansion, for example, carbon fiber, possibly with aluminium or with steel, that does have to be considered in terms of the process. So with the actual joint configuration and position of the joints, and also more importantly the actual how the joint is structured in the CAD design, is a key process. So that needs to be analysed, let's say, in terms of its section, the flange configuration, and the flange joint arrangement needs to be part of that, understood during that design process.
Thanks, Martin. We've got a question here regarding resistance spot welding, which is so widespread and development within that. The question is, what is the profile difference between the electrode used for the aluminium resistance spot welding you mentioned and the one that's currently used for steel? Would the welding parameters for the aluminium be different from the one used in steel?
Yes. The answer to that is they are different, and both in tip configuration and in parameters used. So if we looked at resistance spot weld, traditionally certain OEMs and go for, let's say, a cap, and that would be a truncated or a domed configuration. Okay, chip life can be let's say is greater when we're just resistance spot welding, let's say, bare or standard materials. In terms of the aluminium, it's critical that the joint surface, because of the oxidization of the actual material, the we mentioned earlier about the film being built up on the actual tip surface. So the tip surface is normally a more shallower radius, okay, in terms of its configuration, and also the cleaning process is more critical. So the maintenance of the actual tip to joint configuration, the tip needs to be cleaned on a lot greater frequency, and also because of the material configuration with the aluminium, a lot greater, much greater and higher weld current is required for the aluminium than traditional steel methods. And traditionally, and I'm going to say nearly always, would be a medium frequency configuration in terms of the aluminium process.
Thanks, Martin. We've got a question here, moving on to laser welding and a particular application. The question is, could you elaborate on laser welding in the door opening area? And would that be a continuous or sort of discrete weld, and how would you control the gap within that area?
For a traditional door aperture, and let's say if it was resistance spot welded, tests and production processes we've employed, we've been able to replicate a spot weld, as we mentioned in the presentation, with a stitch weld. Yeah, so it would be a stitched process. And in terms of the gap due to the, let's say, gassing effect, okay, we've introduced a process where we actually, we'll call it pre-process the inner material and produce a dimple, which then has the second material overlaid on top of it. And there's this micro gap which then allows the gases and oxides, etc., to escape out of the actual process, which maintains a good quality joint.
Thanks, Martin. Question here regarding self-piercing rivets. Question is, would they create a problem during the recycling of a vehicle?
The self-pierce rivet, obviously being a different material, yeah, than the aluminium, we'll say, for example. So during the recycle of the complete vehicle, it would have to be separated during the process and broken down separately and identified separately than the overall process. So yes, it would have to be separated from the aluminium-based material.
Thanks, Martin. Question here regarding control systems. Is on FDS process, is this controlled by the robot controller or a specific FDS equipment manufacturer controller?
The controller is bespoke to the actual equipment supplier, and in terms of there is interaction with the robot in terms of position and error messages, etc. But the actual internal FDS process is bespoke to the actual controller of the FDS equipment, because it's a very detailed application and process. That's held within the actual controller itself.
Thanks, Martin. Just a quick, going back to laser welds here, how many remote laser welds per minute? I suppose that's what's the maximum sort of frequency of those?
Approximate, let's say, less than half a second. So you could say approximately 120 a minute, depending upon the process and stack up. So a normal processing time would be actually at the joint of 0.5 of a second or less.
Thanks, Martin. Going back, well, sticking with laser actually and laser brazing, the questions come in, what steps are being taken to ensure the quality of laser brazing of dissimilar metals, e.g. an aluminium roof to a steel body?
Well, like any particular joining process, the parameters and in terms of the monitoring of the process is critical. But from a point of view of the actual understanding the joint quality, coupon analysis will be done prior to production. This would then identify guideline parameters in terms of the process. These materials then the coupons then would be sectioned, etched, and inspected to ensure a robust process was in place. Then once in production, the actual parameters and monitoring process is then studied in a, let's say, an absolute continuous basis in terms of the laser profile and heat source, etc. So it's held in, let's say, a very critically monitored process. And then in terms of post-process, the again the section and inspection of the actual joint.
Thanks, Martin. Question back here relating to Comau's development. I mean, is Comau working towards developing a robotic FSW solution?
Is Comau what? Excuse me.
Sorry, Martin. The question's coming. Is Comau working towards developing a robotic FSW solution?
Friction stir. Comau are currently working on a number of developments, some of which, let's say, are known in the public domain and some are not known in the public domain. And we are reviewing and assessing a large number of process technologies, of which friction stir is one of those processes.
Thanks, Martin. I'm sure that was one of those questions you answered as fully as you possibly could, given the nature of it. We always want to know the real details. Similar question, well, I say similar question, but a question here, again, I'm not sure whether you'll be able to help with this, but what material is being used for plasma transferred wire arc coating that you mentioned in the presentation?
Due to the nature of that process and its, let's say, this confidentiality which exists around that process, yeah, the material, the patented material, I'd rather not discuss at this point, yeah. But if there is an opportunity to kind of have an offline, that could maybe be discussed in some more detail. It's a very, let's say, secure and confidential process that I'd rather not disclose at this point. Okay.
Thanks, Martin, and that's great for us because obviously we're speaking to the people, ladies and gentlemen, who know this information, but obviously are not allowed to broadcast it very widely at times. So I'm sure there'll be time for one-to-one contact following the presentation. Martin, back to aluminium vehicle bodies. The question here: where is steel generally used on vehicle bodies where it's aluminium intensive?
Steel is normally, let's say, within the process design, looked at from a point of view of overall noise reduction. Yeah, so it could be used in terms of, let's say, bulkheads or in terms of rear floors, etc. in terms of the actual process, because the product design teams are kind of doing a fine balance overall between weight, customer demands, noise, engine performance, overall handling and drive performance. So it's a fine balance, but traditionally it's used as in a process where we've got aluminium intensive to reduce the noise and improve the overall performance of the vehicle.
Thanks, Martin. I'll make this, we've got a last couple of questions, but we've got a lot of questions, and what we'll do is we will forward these on to you following the presentation because we're running out of time here. Probably the final question is that's come in is the auto adaptive system. Is this recommended for aluminium spot welding?
Due to the sensitive nature of the let's say of resistance spot welding of aluminium in terms of its critical process, a very robust timer process and control is required. Okay, so traditionally there was you have more scope for tolerance errors and build issues, etc., within a traditional steel environment. Within the aluminium process, it's more critical that monitoring and the maintenance of the actual process are more robust. Yeah. So complete control of the process is absolutely recommended. Okay.
Thanks, Martin. We're going to bring the Q&A session to a close. We've got a lot of questions coming, people requesting material catalogue from Comau, and also the presentation, so we will forward all these requests on to you guys at Comau. Thanks very much to Martin for the presentation. Really interesting stuff and extremely topical, something we've been following in the magazine over the last few issues and continue to watch with interest. Lots of new technologies, which ones will prevail. Adding multi-materials into a vehicle adds complexity, and with choice comes making difficult decisions sometimes, but very interesting indeed. For all of you who have listened today, the seminar, the webinar will be recorded and posted onto our website, automotivemanufacturingsolutions.com, and all our previous webinars are archived there too, and any future ones. Again, ladies and gentlemen, thanks very much for attending, and thank you very much to Martin for his time this afternoon. Thanks very much.
Nick, if I could say just a few words, please.
Yeah.
I would just like to say a big thank you to yourselves in AMS, but also to people who've dialed in either in the morning, the afternoon or the evening out of their busy schedules to listen to the presentation. Thank you very much for your time. Hopefully you found it informative and constructive. And as Nick said, any questions or any information required, we'll make every effort to make sure they're answered. And also, if there's any additional information or visits or coordination required, we're here to help. Okay, thanks again.
Thanks, Martin, and goodbye to everybody. Thank you.